very happy to share with you one of my recent results that is about regularity for degenerate elliptic partial differential equation, including the p-Laplacian as our model. The novelty essentially is in assuming a very low regularity about the data of our problem. So we start as introducing our main motivation. This is a project I am conducting together with Professor Urbano and Professor Temurazian that are located in Saudi Arabia. And the original motivation for this project is that we want to study free boundary problems, but under very minimal assumptions on the integrability of the coefficients. So the first step to this problem is to establish some C1 alpha estimates for weak solution to the equation involved in the problem. So this is our first step, this result. And now we come to our result. And the problem can be formulated as follows. We have a degenerate elliptic partial differential equation that we consider in a variational form, in the Huygens form. And our result is valid for quite general situation, but just to keep the things simple, you can think to the p-Laplacian for a model of nonlinear operator, or if you want a simpler model, linear, you can think to the Laplacian, just take p equal to. What is the novelty is that our right-hand side, function f, the data, is essentially in a bit more than L1. A bit more means that we do not consider just L1 data, but we add some very mild condition. According to my previous experience, I proposed to take the right-hand side in the L1 lambda Morrey space. Sorry. Classical result in the field of PDE about this kind of problems are the very well celebrated results by the Georgi, Nash, and Mosers about Hölder continuity, linear and nonlinear, and also the celebrated results in the book by Lavizeskaya and Uraltseva about C1 alpha regularity, where they consider the homogeneous equation. And after that, there are several extensions to non-homogeneous equations. The first results that appear in the literature considering Morrey spaces are due to Morrey. Sorry, this reference is wrong. This is 1938, the book, the famous book by Morrey, where he states some result for elliptic equations and also systems. And the key ideas, all the ideas, are already contained in those results. The results are in this direction. Coming back to the theory of the 60s, the general idea was that the elliptic equation is like a machine that converts integrability from its data into pointwise properties, such continuity or Hölder continuity. So the idea is that if you want a very good result in continuity or Hölder continuity, you have to push up the exponent for a higher integrability. And really, there are lots of results in this direction. It is indeed true that if you have a very high integrability for the right-hand side or the lower order coefficients, you get a very good result about pointwise regularity. But you can also realize that these results, although they are sharp in the scale of LP spaces, they are not necessary. It is possible to show that regularity is true under very much more general assumptions. General, I mean, you assume a very low integrability. You can have regularity assuming the right-hand side in L1 lambda for convenient lambda, and the value of lambda do not affect the integrability. So morally, you have L1 right-hand side, and you can get quite regular solutions. So the point here is that we want to get a bit more regularity, not just continuity or Hölder continuity. We need the gradient of the solutions to be Hölder continuous. So in the simplest case, if you have just the Laplacian and you have a very good right-hand side, you could even differentiate the equation and then get that any component of the gradient of the solution is a solution to another equation. You apply the usual theory and you get that the gradient is Hölder continuous. But the point is that we want to obtain the result for nonlinear operators and also for operators with variable coefficients. So differentiation is not always allowed. And another problem we faced is that if you have a linear situation, you can also act through some representation formulas, and you can get some result in some very special cases using the properties of the green function. But you know, of course, that in the nonlinear case, we don't have representation formulas and we don't have green function. So there are lots of problems along the way that we were forced to overcome. So our result is, this is the main result. If we have a right-hand side in Morrey space, where you see the exponent lambda is very close to the end of the scale, very close to n, then you get C1 alpha log regularity, and the exponent alpha that you see in the result is strictly connected to all the relevant parameters that are present in the problem. Especially, this is connected to the number lambda. Okay. And how is it possible to obtain such a kind of regularity if you don't have sufficient integrability of the right-hand side? You know, several techniques in PDE, they use very much the integrability of the coefficients because you have a very good environment full of properties arising from functional analysis about duality, representation of the spaces, boundedness for operators arising between LP spaces. If you go to this very weird setting, you assume just L1 for the right-hand side, you cannot use several of these techniques. So our wonderful weapon to fight against this problem is our key tool, the Fefferman Phong inequality. Before coming into details, let me remind you some definitions. I tell you exactly what is Morrey space. It is for fixed parameters p and lambda, as you can see in the statement. You consider essentially the norm of the function localized to a ball. Then you assume some mild condition on the boundary of your domain omega, and you can compare the size of the Lebesgue norm restricted to the ball with the size of the ball itself. So you ask for a kind of comparability between this norm and the ball where it is evaluated. If the supremum of these contributions with the center arbitrary in the domain and the radius arbitrary as the condition allow, then when this quantity is finite, this quantity is a norm, and the vector space that you get with this norm is a Banach space that is called Morrey space. If P is equal to, the space is Hilbert. These spaces are quite well connected to LP spaces. If you take lambda equals 0, you get the LP, the classical definition. If you go to the opposite side of the scale, you take a lambda equal n, you get an infinity. And you cannot take different values for lambda out of 0n, of the interval 0n, because you get trivial situations. So for us, p is between 1 and infinity, and lambda between 0 and n. Oh, these spaces form not a scale with two indices, like a matrix, and there are inclusion relation between them according to the value of the exponent of the parameters. So this is a very simple result, classical. Just use Hölder inequality and the definition, and we get immediately some inclusion between some of these spaces in this matrix. So in this respect, a very important class connected with Morrey spaces is what we call the Stumel-Kato class. That is a space that is in between some Morrey spaces. So I'm giving you the definition. You take an integrable function and fix a number p between 1 and n, and consider the potential generated by this function, where you fix the center of the ball and the radius of the ball. Then you take x and r arbitrary according to our definitions, and you get a function of the radius r. If this function is finite, then you can consider the properties of this function. This function is obviously non-negative and increasing. If this function is increasing, then the behavior in an eyeball of the origin is easy to classify. If the limit as r goes to 0 of this function is 0, then you get the class that we call the Stumel-Kato class. Otherwise, if the eta function is not infinitesimal but just locally bounded, then we say the function f is in the S tilde Stumel class. That is a bit larger. These classes are very useful in working with Morrey spaces because they are in between, as you can see from the next chain of inclusion. So you have that for convenient lambda between n minus p and n, and for any fixed p between 1 and n, this chain holds. And in particular, if you know that your function f belongs to L1 lambda, where lambda is greater than n minus p, then you have an estimate, a precise quantitative estimate of the eta function, of the Stumm-Mercator modulus for f. You can see the Stumm-Mercator modulus is dominated by the L1 lambda norm for the function f, multiplied by an algebraic quantity depending on the radius, so you can measure the speed of how this function goes to zero. So essentially, morally speaking, the difference between the belonging to Stumm-Mercator class and the Morrey space is in the modulus of continuity eta. If you just know that the function is in Stumm-Mercator class, then you only know that your eta is infinitesimal, but you don't know the speed of the zero. If you know that the function is in Morrey class, then an algebraic quantity appears. So this Stumm-Mercator modulus measure how is the speed of the zero. This is very important quantitative point of view. Now we come to our main tool that is very useful to show our result. This is the celebrated Fefferman-Phong inequality. It's very important in an harmonic analysis, and it is ultimately connected also with the indetermination principle arising from quantum mechanics. So from the mathematical point of view, this is like a weighted Poincare embedding, because you have a function f that is in the Stumm-Mercator class and a test function phi in the Sobol space W1T0. And so you can estimate the quantity containing the function f multiplied the test function. You can estimate this product from the integral point of view with the norm of the gradient of the test function multiplied by a quantity. This is the expression of the fact that f belongs to Stumm class. Of course, if you assume your function f in a Morrey space, you have an immediate corollary, because you can quantify the control that you have on the integral, because instead of having just the modulus of continuity, you have this quantitative expression depending on the radius of the ball. So this is our main tool that we use. And another very useful tool is due to Campanato and Meyers. It is an integral characterization of Hölder continuous functions. So if you fix parameter p and gamma, as in the statement, the quantity on the left, that is like an average of the function gradient u minus x average, the ur is the integral average over the ball br, and in general you don't have any information about quantity like this, but if you know that this quantity goes to zero dominated by some power of the radius, r2 power gamma, then the characterization is that the function u is C1 gamma log. This is a characterization, so this is if and only if. So the idea is that if we want to get C1 alpha estimate for our solution, then we could use this characterization and work with the integrals. So now we come to our problem. So this is the problem. I state it for the p-Laplacian, but this is true also for more general operators. So if we consider as our model operator the p-Laplacian, this is what we reasonably ask as a definition for weak solution. So we fix p between 1 and n, fix some lambda between n minus 1 and n. And what we mean by weak solution is an element of W1P, verifying this integral identity for any test function. Of course, it is good to know that the integrals appearing in the definition are all finite, and essentially our attention moves to the right-hand side, because f is in general just an L1 function. It does not have some extra integrability. So to realize the right-hand side is finite for any function phi, then we need to use the Fefferman-Phong inequality. So this is a simple application of Fefferman-Phong inequality. We can realize the definition makes sense. So this is our statement, assuming lambda between n minus 1 and n, and the right-hand side in FL1 lambda, the Morrey space. And gamma is some regularity exponent for the corresponding homogeneous equation that I will tell you exactly later. Then, if we consider the equation of Laplace u, p Laplace of u equal right-hand side f, then we have the solution, the weak solution is C1 alpha locally, where alpha is a number related to all parameters into the game, especially it is related to the number lambda, so it is connected with the right-hand side. Gamma is the regularity exponent of the related to the solution to the homogeneous equation. Okay, so we cannot go better than the homogeneous equation, because in the homogeneous equation the right-hand side is the best we can have. 0 is the best function. It belongs to any space. So we cannot get a result that is better than the homogeneous equation result. So the comparison is between alpha and gamma. But if numbers are well suited, then we get this precise quantitative regularity estimate. Just a sketch of the proof, very, not very detailed. We start considering homogeneous equation and an approximation lemma between the homogeneous problem and the non-homogeneous problem. So we consider, we take our solution U and consider an auxiliary Dirichlet problem. As equation, we set the homogeneous equation, and we look for the homogeneous equation solution such that on the boundary of the domain, it takes the values of the original solution. So in this, under this assumption, we know that there exists a unique solution to this problem for some particular number gamma, depending on the data of the problem. And this is a classical reference in the PDE theory. So now we start we try to prove the C1 alpha regularity for our solution. And the idea is to stay close to the solution to the homogeneous problem. So, according to Campanato-Meyer's characterization, our goal, our technical goal, is to estimate this quantity if we show that this quantity as a function of R goes to zero in an algebraic way, then essentially we have the result. So our idea is to decompose this integral in several pieces, trying to use Fefferman-Phong inequality and information about homogeneous problem. So you can see our integral is decomposed adding and subtracting the gradient of V, where V is the homogeneous equation solution. So we get these three I1, I2, I3 integrals, and our goal is to estimate the three of integrals in the same way. So we start by we start considering number two. Okay, so using the fact that V is the solution to the homogeneous equation, we know that this function is C1 gamma for some gamma. So in this case, the estimate is automatic due to classical information. And so I2 is done. Regarding I3, we make some easy calculation by using Hölder inequality, and after that, okay, we sorry, one moment because okay, I2, I3, okay, we start with Hölder inequality, okay, and now we take the original problem, our original problem, and use u minus v as a test function in our problem. So if you use u minus v as a test function in our problem and consider the homogeneous equation satisfied by v, and then perform some very easy calculation, we get this integral formula. This integral formula that is very good for us, especially in the right-hand side, because the right-hand side contains the datum f and some function that can be used as a test function in the Fefferman-Phong inequality. So at this moment, the right-hand side is not the problem. At the moment, the problem is on the left, because we have this expression, nonlinear expression in the exponent p, and we would like to go below from the left in order to get some quantity related to integral I1. So for this reason, we separate the situation p greater than 2 or p less than 2, because there are some different technical inequalities, elementary inequalities. For example, let us see what happens in the case p greater than 2. We are using this elementary vector inequality, and simply using this expression, we can replace the integral on the left with the integral of the p-norm of the difference of the gradients. So the p-norm of the difference of the gradients can be estimated with the integral that you can see on the right. Now we are almost ready, because now we can estimate the integral appearing on the right-hand side. Of course, in the previous inequality, I forgot some modulus, sorry. But Now we consider the right-hand side integral, and we start try to use Fefferman-Phong inequality. In order to use Fefferman-Phong inequality, we need the test function to some power p and the original function f to the power 1. So we need a simple trick in order to modify our exponent. Here, what helps is Hölder inequality. So we start with Hölder inequality. We get this product of two integrals. The first integral, we can estimate it by using the definition of Morrey space. So Morrey norm in L1 lambda appears. And for the other integral, the one that you can see first line on the right, you can estimate it by using the Fefferman-Phong inequality. So this is the estimate, and we can conclude that the integral I1 can be estimated as you can see in the bottom line. So you see there is this difference of gradients in p-norm estimated, controlled by a power of the radius of the ball multiplied by the norm of the function in L1 lambda. For the case p less than 2, the situation is a bit more tricky, but essentially the idea is the same. The idea is to use some vector inequality in order to go below the integral on the left. And on the right, you can argue as before by using the Fefferman-Phong inequality. So this is the replacement of the calculation in this case when p is less than 2. And in any case, you get the same control. You have that the difference of the gradients in p-norm is controlled in an algebraic way, and depending also on the norm of the function in L1 lambda. So now you can put together the three integrals, and because you remember at the beginning, the goal was to estimate this quantity that appear in top line in an algebraic way. And if you put together the I1, 2, and 3, you get this kind of control where you have this precise exponent alpha that I marked in red. So by using the characterization of Campanato and Mayes, then we got our goal. So the solution is C1 alpha. There is, of course, a natural question arises. The question is, how sharp is this result? Okay, so to measure the sharpness of the result, we can consider this particular example. You have the p-Laplacian equal this function that apart from the constant you see is a radial function. Then you get that f is in L1 lambda, where lambda is exactly this number that is less than n minus 1. And on the other side, you see that the solution is a power gamma, or radial function. Solution is a bit regular, but not so much because the gradient is not regular. So this means that our assumption that lambda must be taken greater than n minus 1 cannot be relaxed. The result can be extended, of course, to some quasi-linear operator in some class that includes the p-Laplacian. So this is quite standard assumption in the nonlinear PDEs. You consider divergence form operators where A is a function let's say, of the gradient. And we put some assumption on A in such a way that this operator extend p-Laplace operator. So, of course, we cannot consider the most general nonlinear operator, but if we assume some reasonable conditions on A, and on the right-hand side, we can put f as in our case in L1 lambda, and we can also consider other function related to the lower order terms. So f is the source, but you can have the g, the potential term, and also the drift h. On the drift, you assume LP lambda, the same exponent of the p-Laplacian, while potential and source term can be taken in the more general space L1 lambda. Essentially working as before, essentially the proof is the same, you get the same result, where of course the number alpha is a bit more complicated. And this is the result. As a possible extension of this result, of course, you could consider elliptic systems or the parabolic case, or also some fractional operator could be considered. But the goal, the final goal is to apply result for some free boundary problem, so for some obstacle problem. And so this is some reference. I can share slides with everybody after the meeting. And that's it. Thank you for your nice, kind